In the previous video we looked at graphical interpretations of electric field strength and potential in between uniform plates. We're now going to take that a little bit further, and we're going to consider a point charge. And there's going to be a few tricky bits about this, but I'll talk you through it. So if we consider a point charge, as we've seen before, we'll consider a positive. So the field lines around a point charge radiate outwards, and that means that the field strength decreases with distance. Instead of using D here for distance, we're going to use R for the radius, so how far away it is. And hopefully you can recall from the subtopic 5.1 on electric fields, the equation that we've got for the electric field strength around a point charge is given as E is equal to KQ on R squared, where Q is the charge that we're dealing with here, and as I said, distance R is the radius or the distance away, and you might recall as well that the value of K is equal to 1 on 4 pi epsilon naught. I'm not going to go back over that here, but just as a quick reminder. Now, if we were to graph the electric field strength versus the distance away from the charge, so in this case we're looking at distance from the charge now, and the units there would still be in meters, and on the vertical axis we're still going to look at electric field strength. The shape of that graph is going to be an inverse square, and we'll still use units here of volts per meter. So the shape of the graph will look something like this, where it gets closer to both the vertical axis and the horizontal axis. Now if we just refer back to what we were talking about with the uniform fields, we could actually look at moving from, say, one point, so let's imagine this is a distance R that we're looking at, and we're going to some other distance over here. I'm going to call it R1. So the area here would be the potential difference when moving between R and R1. So that area is gives the value of the potential difference. And notice, if you think back to what we looked at, that will actually give you a negative value. And the reason for the negative here is that around a positive charge, you're actually going to be going to a lower potential when you move away. So you'll the potential difference will be decreasing, or will be smaller. So that would be the potential difference moving from R to R1, but we don't always want to know what potential difference is. Sometimes we want to know what the actual potential is at a point. So in other words, instead of looking at say the area between R and R1, we might actually want to look at the area from R all the way up to infinity. So the red area there, if we find that area, that will give the electric potential at a distance R. Now here's where some of the tricky bits come in. Keep in mind that we were looking at the idea that the electric field strength is given by the equation negative delta V on delta D, but here we'll change that to delta R, given that R is the distance we're looking at. In order to now explain this in a bit more detail, we need to use some calculus here. This process is not one that you need to memorize. It's not one you need to actually even understand at this point. You will get onto some of these mathematical procedures in your maths subjects, but I'll just use them here to identify how we get to the next result that we're interested in. So in calculus form, we'd write this equation as dV on dr, and we've already seen that that equation for electric field strength is given by KQ on R squared. So what we're really doing when we are finding that area under the curve, we're really integrating from the value of r up to the value of infinity. So we're using or not the value, up to the limit of infinity. And just to do that, we'll take this the expression here, we'll actually throw the negative across the other side to make it a little bit easier to work with. So when we go through and integrate that, we would initially write it as that we're integrating from r to infinity for the expression of negative e, and we're integrating with respect to the variable r. And as I said, these steps, not important for you to memorize, but just wanting to draw your attention to the derivation of this next equation. One of the useful things that we can do now is, because we're looking from r to infinity, this process actually works a little bit better if we reverse that, and so we look from infinity to r. When you do that, there's a rule for integration that means that you're actually going to find the negative of that. So we end up with that as our next line of working. Notice we've now got two negatives here, so those two negatives cancel. So that's quite convenient. So we're really looking for the integration of this equation E, which is kq on r squared, integrating with respect to r, and skipping a couple of steps that you don't really need to see here, but again, follow what you'll cover in maths and you'll be able to make sense of it. We end up then with the relationship that V is equal to kq on r. If you are more interested in how you go through that process, I can run through that in class with you. So we now have another equation here that tells us something about electric potential around a point charge. So notice I'm highlighting that one, it's in the data booklet. That means that we now have a graph that we can produce for electric potential, so not potential difference, just electric potential at any point in a field around a point charge. And we'll still have, in this case, distance from the charge, and that distance is r, and it's measured in meters. And notice now the relationship is an inverse proportion, so V is inversely proportional to R. So the shape of that graph will look somewhat similar to the electric field strength, except it's not quite as sharp a turn in the curve. It's a little bit flatter, but we ultimately end up with that graph. Now we're going to flip this back around once again. If we look at the gradient here, so I'll just make this note down here. The gradient that we're dealing with is going to be change in potential over the change in distance r. And we already saw that in the previous video that the gradient actually, or the negative of that gradient I should say, gives us the value of the electric field strength. So in this particular scenario, if we were to imagine a point here, I'll just change colour to make this a bit clearer. The gradient at that point would be represented by that tangent, and so we could then identify that this value here would be the change in the electric potential, and that value would be the change in the distance. Notice there that the gradient is actually negative, so when we find the negative of the gradient value at that point, we get a positive, which is what we would expect around a positive point charge. The field is radiating away from the point charge. We'll have a look at a few more questions in class dealing with electric potential and how it relates to electric field strength, but just wanted to draw your attention to how that equation sort of links in when you're dealing with a point charge, whether the field is no longer uniform. One last point to note about this scenario of dealing with electric potential. If we do work on a charge, so doing work to move a charge against a field, or another way of stating that, if we're doing work against an electric field, what we're doing is moving it to a higher potential. What we're really doing here is giving it some energy. So in doing work it's gaining energy. The charge in this case will gain electric potential energy. Now, you might have heard of gravitational potential energy before in previous science units. We will actually get onto that when we come back and look at gravitational fields. But electric potential energy is basically just energy stored by a charge due to its position in an electric field. So if we raise it to a higher potential, it means that if we let go of it, it could then start moving, and that electric potential energy would be converted into kinetic energy. So if we look at that scenario, W is equal to QV is the equation that we've been dealing with. So the work that we do is equal to the charge multiplied by the potential difference that we move it through. What we're now saying is that electric potential, that work that we do is also the same as potential energy. Notice here that we're using E for energy, so don't get confused between electric field strength and energy. The subscript P makes it a little bit clearer to indicate that we're looking at potential energy. Now, if you look at that expression Q times V, we've just seen that V is equal to KQ on R around a point charge. So we can make that substitution. Instead of writing V, we can now write KQ on R. And so this equation then becomes KQQ over R. So there's our electric potential energy around a point charge. Note that it looks somewhat similar to Coulomb's law, F equals KQQ on R squared. We can actually link those two together, identifying that if we've got F equals Q times E, electric field strength is equal to KQ on R squared, so that could also be expressed as KQQ on R squared. So notice there's a similarity there, but when we're looking at work in terms of force, work is equal to force times distance. In this case, we'd look at the value being R, and so that would then give us KQQ on R. So there's all of these equations are linked together, but ultimately the electric potential energy is the one that you need to relate to there, and you can tie that back into the force on a charge in a field.